Out of nowhere, Google rolled out Project Suncatcher, a research moonshot to explore running ML compute on solar-powered satellites in low Earth orbit. It's not a consumer product or a cloud SKU yet, it's a research program with prototypes planned. It is the 5th of November, 2025, and you're watching the Daily Dose of AI. This competes with the on-Earth data center arms race, AWS, Azure, Nvidia racks, and other space compute startups that are already testing GPUs in orbit. The headline: Google wants to move some AI compute off Earth to address power and cooling limits, but that's a long, expensive, engineer-heavy road. Why now? AI models keep ballooning, and data centers are hitting limits: power caps, water use, land, and cooling overhead. Google's paper frames Project Suncatcher as a way to tap space solar and dense satellite networking to supplement Earth compute, not replace it overnight. The company says prototypes, 2 test satellites, are targeted for early 2027. That's a milestone, not a commercial launch date. Google proposes a modular constellation of smaller satellites carrying ML accelerators, TPUs, and interconnected by free space optical links, lasers. The idea: network them into a distributed space-based ML fabric. Power: panels in orbit get higher instantaneous solar irradiance and can produce more annual energy per panel than mid-latitude Earth panels. But LEO satellites still experience eclipses each orbit, so usable energy depends on orbit, duty, cycle, and storage. The company's paper notes up to approximately 8 times higher annual irradiance compared to some ground locations. That's a conditional claim, not a universal free energy magic. Latency and bandwidth: being an LEO reduces round-trip delay compared to GEO satellites, but real-world latency depends on routing, ground station density, and atmospheric effects on optical links. Tens of terabits per second intersatellite capacity is an engineering target for laser constellations, not an immediate guarantee. Hardware in space, radiation hardening, thermal control, and reliability trade-offs matter. TPUs will need shielding, error correction, and redundancy. You can't drop a server rack into orbit and call it a day. Google explicitly calls these significant engineering challenges. Google frames this as long-term research. Their cost parity scenarios rely on assumptions about launch costs dropping and on-orbit reliability improving. A plausible projection, but speculative. Meanwhile, players like StarCloud/Crusoe are already experimenting with GPUs in orbit, meaning Google is joining an active but risky trend. If it works, you get new compute geography and less terrestrial grid strain. If it fails, you get a multi-billion-dollar engineering exercise and a lot of astronomy complaints, satellite interference. This ramps up the infrastructure moat. Winners will be the firms that can afford the R&D and regulatory fights. Also, expect debates over spectrum, export controls, and national security. Space compute isn't just tech, it's geopolitical. Don't re-architect your product to assume orbital compute tomorrow. Watch Project Suncatcher as a 5 to 15-year infrastructure narrative about power, latency, and monopoly building. Smash the like and subscribe if you want more deep, sarcastic breakdowns. And the open question: who owns the orbit compute stack? Tech cartel or wider public utility?